Hey everyone, hope you're having a great day today. We're going to finish up the notes from yesterday on polarity and hydrogen bonding. So first, we've talked a lot about covalent bonds, but now we're going to talk about two specific types of covalent bonds. Those are nonpolar and polar. You got to be really careful to keep these two separate because nonpolar and polar are tricky words. You're just going to have to know which one is which. Here's what you need to know about nonpolar. Nonpolar means that there is exactly equal sharing of the electrons. An example of that is a bromine molecule. So that's two bromines bonded together. They both pull on the shared electrons the same, so it's equal sharing. You usually have equal sharing when you have two of the same type of atom because they have the same pull on the electrons. We call that the electronegativity. So it's an equal share. However, if you take two different atoms and they're sharing the same electrons in a covalent bond, it's pretty likely that one of them is going to pull more strongly on those electrons than the other. And that's going to create a polar covalent bond, which means you have unequal sharing of electrons. So the trick is non-polar is equal, but polar is unequal. You just have to remember that. Another name for polar bonds or polar molecules is called a dipole. Di means two, pole means pole, like positive and negative opposite charges. So polar covalent bonds create dipoles, opposite charges. So there's a chemistry way of showing this because obviously, chemists are lazy in the best kind of way. We're not just going to write polar every time. We use these symbols. Always love using a nice little Greek letter. We use delta plus and delta minus. And if you remember delta from math class, you might have seen the triangle looking thing. This is a lowercase delta. So it still is a delta, it's just a little bit different. Um, and the reason we use delta is it's not a full positive charge, it's not a full negative charge. That would be like an ionic bond. But remember, one atom is not completely taking the electrons away, it's just sharing them more or losing them more. So the one that pulls more strongly is going to have a delta minus and be a little bit negative. The one with the weaker pull or the lower electronegativity is going to have a positive charge because it doesn't have as much pull on those electrons. So you can probably guess this is from like a long time ago, but yep, check it out, still relevant. That's why I love chemistry. This is what electronegativity is all about. Electronegativity says how strongly an atom is going to be able to pull on those shared electrons. So more electronegativity means a stronger pull, which means those electrons are closer, which makes it a little negative because electrons are negative. All those things kind of go together. And those wonderful electronegativity arrows that you drew on your periodic table, yup, you're going to get to use them now. So here's a table showing the numbers of all the electronegativities. Notice that this follows the arrows that you drew. Electronegativity increases as you go from left to right, and then it increases as you go from bottom up to the top. There's a couple slight exceptions on here. But in general, those arrows are true. Also, this is like a British table. So these little commas, we would write those as decimal points because they flip their decimals and commas. But if you're looking at this slide, don't let that confuse you. Like this right here, cobalt is 1.70, not one comma. That's just the way they do things. So if you wanted to label these, I'll do one. And then if you want to push yourself, you can pause the video, try to do the rest of them. You're going to need either the arrows on your periodic table or this handy dandy one I got right here. So find these two atoms in this bond. If we have a bond between nitrogen and hydrogen, let's see, here's nitrogen. It's got 3.07 and hydrogen is 2.2. Nitrogen has a greater electronegativity, which means it's going to be a little bit negative. Hydrogen has less, meaning it'll be a little bit positive. So we write the delta negative over nitrogen, the delta positive over hydrogen. You can pause, check out the table, look at your arrows, and see the rest of them, and I'll go through the answers here. So pause now if you're going to. Come on, you didn't pause? Well, I warned you. All right. Anyway, so here's aluminum and phosphorus. Aluminum, we got 1.47. Phosphorus is 2.06. Chlorine and hydrogen. Chlorine has the higher electronegativity at 2.83 compared to 2.20. Hydrogen and oxygen. Hydrogen's partial positive, oxygen partial negative. You might remember that one from biology class. And lastly, the bond between carbon and chlorine looks like that. Chlorine is 2.83, carbon is 2.5, which means chlorine has a higher electronegativity, which makes it a little bit negative. Next, you can talk about polarity of an entire molecule, not just a single bond. So when you talk about the whole molecule, it depends on the bond and how strongly those two electrons are pulling, but it also depends on the shape of the molecule. And I'll show you some examples in a second. Because even if you have polar bonds, if the molecule is the right shape, those different poles and positives and negatives might just cancel each other out. A great example is water. Hopefully you remember water is polar. I've said it like 100 times. Hopefully your biology teacher said it 100 times too. Here's some pictures. So these are two pictures of water. Notice that the examples we just looked at are just a hydrogen and oxygen bond right here. So we said oxygen has more electronegativity, which makes it more negative. So if you take the whole shape of the molecule, the oxygen end is going to be a little bit negative. The hydrogen end is going to be a little bit positive. And basically, sometimes if a whole molecule is polar, you'll see an arrow like this that points to the negative end, points away from the positive end. And each bond right here, all we're doing is taking these two little blue arrows and adding them together to say the whole molecule is polar. So this, and this are three different pictures of water showing how that works out. Sometimes if you're fancy, you get to put a little cross at the end of the arrow. So that shows you the plus side and it points to the negative side. Over here is carbon dioxide. This whole molecule is nonpolar, even though it has two polar bonds in it. That's kind of confusing, but the answer is all about the shape. If you zoom in and just look at the carbon and oxygen bond, you'll see oxygen has a bigger electronegativity, so it pulls the electrons away from the carbon, making the oxygen just a little bit negative. So our arrow points towards the oxygen. And then the plus side means the carbon is a little positive. But when we take these two bonds and we draw the arrows, they're the same strength and they point in exactly opposite directions. So if you added those together, they will completely cancel each other out. So even though the molecule has two polar bonds in it, the whole molecule is said to be nonpolar, or you can just say there's no net dipole, same thing. Here's an example of what happens when you take two molecules that are polar and put them next to each other. There's going to be this type of bond that holds the molecules together. This is not an ionic bond. This is not a covalent bond. You've got covalent bonds here, covalent bonds here. That's what's actually holding the atoms together. This is a new type of bond that's happening from one whole molecule to another whole molecule. And the fancy term is intermolecular forces. Inter just means between. Molecular means molecule. So this word is just really forces between one molecule and another. And like I just said, covalent bonds are what hold the atoms together within a molecule. But now we're looking at molecule A, molecule B. What holds those two molecules together? Those are not as strong as covalent bonds or ionic bonds, but they can still cause some pretty important properties. And like I said, intermolecular forces. One type of intermolecular forces is van der Waals forces, but we don't really have to worry too much about those. The most important type of intermolecular forces is hydrogen bonds. Hydrogen bond is a specific kind of intermolecular force that happens between hydrogen and on the other end, so hydrogen on one molecule and on another molecule, fluorine, oxygen, or nitrogen. You can always remember that and just think like hydrogen bonds are fun. You can do your best Arnold Schwarzenegger. We're having fun with chemistry. Hydrogen bonds are fun. And that's how you remember it. So here are some drawings here. If you were going to draw some hydrogen bonds, I'm not going to sketch them all in, but remember for each of these, the oxygen is a little negative. Hydrogens are a little positive. So every hydrogen bond is going to happen between a hydrogen and an oxygen. And usually you show those as dotted lines. Negative to a positive. Here's a positive to a negative. Dotted line here. You can have a dotted line here. You would not have a dotted line between these hydrogens because those are both positive. Like charges repel, opposite charges attract. Same deal here. You could have hydrogen bonds, but remember those have to be between hydrogen on one molecule and a FON, F-O or N, on another molecule. So you could have one here if you wanted, dotted line. You could have one there, dotted line. Let's see, there would be a good one for a dotted line, but it should be from a positive to a negative. And I'll let you draw the rest of those in. And just like a good mirror, let's end with a little bit of reflection. Answer these questions on your paper. How does the activity with the penny that we did yesterday demonstrate surface tension? If you weren't there, ask one of the brilliant people at your table what happened when we did that. How does soap affect the hydrogen bonding of water? Justify your answer. Schmidt's hint on that one, soap disrupts the hydrogen bonds, makes the hydrogen bonds not happen. Tell me why that is. And then finally, when water's on wax paper, is that an example of cohesion or adhesion or maybe even something else? So I'll let you think about those questions. And when you finish this, double check the old Schoology Power School, see if you have any missing assignments. If you have any questions, send me a message. And thanks for watching today. I had fun. I hope you did too.